What we're going to do today is a practice quiz, but it's really not meant to grade you, really. I mean, everyone should get 100%. I really just want to make sure that everyone's going through the process. They're able to do the basic problems correctly, so you're prepared for the homework. It's also a really good time, since I've only given 4 problems, where if you run into difficulties, um, you stop and ask. So if you're not understanding something, just let me know. We'll stop and go through it. Okay. Now, this was designed as a quiz in Pearson, which means you won't know your score till you're finished, but we'll probably finish a little bit early. So if you missed some problems, I'll stay after and we can look at them and correct them, and you'll get full credit for that. Okay. Okay, so let's go ahead and get started. Give me 1 second. I need to go through a different link than you guys do. So give me 1 second here. Okay, here we are. Okay, so here's our first problem. It asks us to find the most general antiderivative. That's kind of a misnomer. There is no thing as the most general. They're just trying to make the point that they want you to find the general antiderivative or indefinite integral. Okay. So this should be my primary screen now. Yeah, my dot cam. If you're not seeing it, let me know. So we want to find the general antiderivative or indefinite integral of uh, I should really say 4 here, okay? And this is our problem. Probably not a bad idea to kind of write these problems down in your homework notebook, because they may help you do the homework problems. Now, we covered indefinite integral at the end of last class, so let's just kind of refresh our memory. Indefinite integral and the general antiderivative, they are equivalent things, okay? So I can say one thing or the other. Now we're going to tend to start to talk about the indefinite integral more. And the reason why is because with the indefinite integral, we have a notation that's associated with it. And this is how we're going to start writing these problems, okay? So even though when we started off, we were talking about the general antiderivative, now we're going to use the equivalent name for it, which is the indefinite integral. So the first thing we want to do, and you can do this on your problem, just kind of work along, is we want to look at the form. And you remember with the form, we're always talking about arithmetic, right? Are we adding, subtracting, multiplying, etc.? And here you can see that in this thing that I'm trying to integrate, I have a sum. And so that tells me I'm going to break up the indefinite integral into two indefinite integrals, because we remember that antiderivatives or indefinite integrals, they distribute over sums the same way that the derivative operator did, right? So we're going to get now two things to notice. First of all, be a little careful. Sometimes with the problems, when you're working with t's, they look like ones. Every once in a while, I'll make that mistake myself. So make sure that you clearly distinguish what is a t and what is a one when this is the variable you're working with. The other thing that I want to draw your attention to is you want to make sure that you put the differential in. One of the things that will lose you points on exams and on the final is if you don't put the differential in. And it's going to be important later on. Okay, our next step, we're going to look at this and we're going to realize that in both cases, we have a number multiplying our function. Now, after a while, you won't do this, but when we first start working these sorts of problems and learning how to do it, it's not a bad idea to factor out this scalar multiple, right? And you'll notice that for the t over 6, I'm going to rewrite the integrand as 1/6 times t to the first. And of course, I'm going to pull that scalar multiple outside also, which will give me okay. And of course, we do this initially because now we can really just focus on the function that we're integrating. And we notice that both of these functions are power functions, right? And they're not 1 over t. That's a special case. We might remember that when we take the antiderivative or the indefinite integral of 1 over t, we get natural log of absolute value of t. But in this case, these are going to be power functions. And we remember the rule for integrating power functions. It says if I integrate x to the n, I'm going to basically increase the exponent by 1, divide by that same number, and add c. So this is our integration formula for power functions. I can't emphasize enough how important it is to learn the integration formulas as soon as you can. Not only will it help you do the homework, it'll help you on the exams where these things have to be second nature. You don't want to try to cram and do this at the last minute. Moreover, in MA 242, 2/3 of the course is integration. So really the time that you invest memorizing these is really going to do you a lot of good. Well, if I apply this rule to the first integral, right, my n here is equal to 3. And so if I increase this by 1, this will be t to the 4 divided by 4. And be careful, by the way, and I do this sometimes myself when I'm rushing, I'll sometimes put x in when the variable of integration is t. So make sure you don't do that. So here it's going to be t to the 4th divided by 4. And then I'll have the 1 over 6. And we realize this is actually t to the 1st, right? We don't write an exponent. And of course, if this was 1, this would be t to the 2nd power divided by 2. Now, super important, don't forget the cherry on top, right? With that plus c. And so I'll mention that the two things you want to watch out for at this stage is, first of all, make sure you simplify. Some people on the last exam lost points just because they didn't simplify things down. So this first term, for example, I wouldn't leave as 4t to the fourth over 4, right? I would go ahead and I would cancel out those 4s. And now we simplify it, and that should be our answer. So go ahead and work that out and into your result, okay? Now you can check your answer at the bottom, I believe. Do you guys have the option of checking your answer?
No.
Okay, so we'll have to submit it. As I said, if you get it wrong at the end, we can go back one-on-one, look at it, figure out what you did, and you can get credit for that, okay? I think next time when I make the quizzes, I'll construct them as homework problems in my math lab. That way you can check problem by problem as we go on. Okay, is everybody good on this problem, or are there any steps that we want to talk about a little bit more? Looking good? Okay. So in that case, let's go ahead to the next problem. Which is going to be an initial value problem. I'll show you mine. Yours will be slightly different, right? So it says solve the following. And everybody abbreviates initial value problem, IVP. So this is how we abbreviate it in mathematics. So I'm just going to abbreviate it like that. And so here's the statement of the problem. Remember, with an initial value problem, we have to have a differential equation. So this is our differential equation. Which is just a mathematical way of saying we have an equation that has a derivative in it. Now, when you have a second order derivative, you need two initial conditions, one on the first derivative and one on the function. So these are our two initial conditions. We're told that the derivative function evaluated at 0 is equal to, and in my case, the answer is 4. And then we're told the function itself evaluated at 0 is some number, which in my case is 5. And these are our initial conditions. So this is our given information. And what we want to do with that given information is we want to find the function y. Now, we had a problem like this yesterday. You might remember we had a problem involving acceleration, which is another second derivative, in that case of the displacement function, right? And we were given an initial velocity and an initial displacement. Here we want to treat this problem the same way. The first thing we're going to undo is we're going to undo the first derivative, and we're going to solve for y prime. So first, we're going to solve for the derivative function. And the way we're going to do that is we're going to integrate the second derivative. So by integrating, we're taking the antiderivative of the second derivative. And let's see what happens when we do that. Now I'm going to use the anti-D this one time because I want to illustrate what's going on here. So on the left-hand side, who can tell me what we'll get? What happens when I have an antiderivative and a derivative?
Cancel each other.
Exactly. They're inverse processes. And so notice what we're doing is we're kind of like undifferentiating the problem, right? This is a way of kind of unraveling the problem. So those two undo each other, so to speak. And I'm left with y prime of x. Now, what is the antiderivative of 0? So how do we answer that question? What is the thinking here?
It would just be c because c is any integer, and then the derivative of an integer is just 0.
Right. What you're asking is, what function, when I take its derivative, do I get 0? And the answer is a constant.
One C.
Bingo. Exactly. Okay. So now we have the general antiderivative. Now we're going to use the initial condition. Notice we have two initial conditions. Well, I'm interested in the derivative function, so I'm going to use the initial condition on y prime, right? Sometimes people, when they do these problems, sometimes students are a little uncertain about the fact that we're going to do this twice. So we're going to get two C's. So sometimes people call this C1. It doesn't really matter, but if you want to do that, you can. Okay. So on the one hand, the given information tells us that the derivative function evaluated at 0 is equal to 4. Of course, you're going to have a different number, right? But what we saw from taking the antiderivative is that the derivative function everywhere, and therefore at 0, is equal to this constant C1. And so we can see from that, pardon the pun, that C1 is equal to 4. And of course, the next step is I'm just going to sub this into my original general antiderivative, right? And of course, when I put 4 in for C1, I'm going to get that the derivative function is equal to 4. It's a constant. Okay. Of course, we already know there's only one function whose derivative is a constant everywhere. That's a line, but let's go ahead and work this out because it's not going to be that way for every problem, right? Okay, so now I have the derivative function. I'm going to play the same game and I'm going to find the displacement function. So first I'm going to undo the derivative, and now I'm going to write the indefinite integral. I'm not going to write anti-d. Okay. Eventually, we want to kind of wean ourselves away from writing stuff like anti-d. Nobody writes that, okay? So I'm going to take the indefinite integral of both sides. Notice when I take the indefinite integral, I need the dx along with it, right? Of course, this side, we know what happens, right? This is an antiderivative of a derivative. They're going to cancel. And so I'm going to get y of x. And again, you can approach this two different ways. The one way is to say what function, when I take its derivative, gives me a constant. And we know that's a linear function. It's the constant times x, right? If you don't like that and you want to kind of do this old school, right? Okay, you can go ahead, you can factor out the 4, and you can use the fact that the 1 is really x to the 0, right? And now you can use the rule for taking the integrals of power functions, right? This would be x to the first over 1, and you'd get the same result. Now I'm going to apply the initial condition. And this time we're going to use the initial condition on just y. So on the one hand, we're given that y of 0 is 5. And you can write down whatever it is for you. On the other hand, if I plug 0 into here, I know that y of 0 is equal to c2. So of course, this tells me that c2 is equal to 5. And finally, I just plug the value for c2 in. And that's my final answer. So it's kind of a long problem, but go ahead and work that out for your question. Now, notice that if you wanted to check your answer, how would you do this? Well, this solution has to satisfy these 3 conditions, okay? So here would be our check.
Professor, I just have a quick question.
Yeah,
When we're entering the solution, do we put y of x equals because it's a type of equation?
yeah, that's a really good. So let me. So it's such a good question. I'm going to stop what I'm doing and answer that. So the question is, when you enter your answer, how should you do this? Should you do it like, what was mine? 4x plus 5? Yeah. Should you write it like this? Should you write it like this? Or maybe you should just write it like this. And of course, you wouldn't know ahead of time. So the correct answer is that. So don't write y of x because it will mark it wrong. Okay. Now, suppose we want to check our answer. So the check would be that we're claiming the anti-d. I'm sorry. Sorry. We're claiming the function y equal 4x plus 5 is a solution to the IVP. So this means that y equal 4x plus 5 has to satisfy 3 conditions. So it has to satisfy the differential equation. and it has to satisfy the two initial conditions. Whoops, 0, sorry. So this is what you would check. You'd check that the second derivative is 0, and you can see that it is, right? When you take the first derivative and you put in 0, you're going to get 4. When you put 0 into the function, you'll get 5. Okay. When you take differential equations, you learn that there's only one solution that can satisfy all three of these. So this solution is unique. There can't be any others. It's like Highlander. There's just one, right? Okay, any questions on this before we move on? All right, good.
Can you go back to the last page?
That guy there?
Yeah.
Mhm. Whoa.
Okay.
Excellent. Okay, so let's look at problem 3. So we want to evaluate the indefinite integral of -7 times cosine of t. So again, the first thing your eye goes to is the fact that you can factor out a scalar multiple. So I'm just going to write this as -7 indefinite integral of cosine t. Now, how do you find out what the indefinite integral of cosine t is? How do we do that?
We have our rules.
Yeah, so you could use the formula sheet, right? That's perfectly fine. The other way you could ask is, what function, when I take its derivative, gives me cosine, right? And what would that be?
Sine.
Yeah, so that's going to be our answer, right? Okay. So you notice that the integral rules are really just the derivative rules in reverse, right? That's all they are. Sine t. Then don't forget to put the cherry on top. And that's our answer. Now, let me show you a little trick that can help sometimes. Suppose you're on the exam and you have a brain freeze. You say, I have no idea what the integral of cosine is. However, you know the possible choices, right? And I'm going to list the possible choices for my problem set, okay? So the first choice is minus sine 7 times sine of t plus c. This is minus 7 cosine t plus c. So these are the possible choices. How can I tell which of these choices are correct? Suppose, like I said, suppose I'm not good at integrating, but I know how to take the derivative really well. how could I determine which of these is the correct choice?
Well, first you can eliminate the ones that have cosine in it.
Yeah, that seems like that's probably not going to be the right answer, right? But then I still got 3 choices left. So how could I know for sure? Well, what if I take the derivative? So notice if I take the derivative of everything, right? Here, I'm going to get minus 7 cosine of t. So I can take the derivative of all these and see which one gives me minus 7 cosine t. Of course, the very first one, it just happens, gives us the right answer, right? But the derivative of cosine is minus sine, right? So this would give me 7 sine of t. 1 over sine is cosecant. And when you take its derivative, you're going to get minus cosecant minus cotangent, right? And then, of course, derivative of sine is cosine. Okay. And so if you don't integrate well, but you know how to differentiate, you can still get the right answer. Now you might say, well, this problem is so easy. Why would I ever do that? And that's a valid point. But what we're going to see 2 weeks from now is that the problems won't be as easy, and you won't be able to look at it and see what it is. So this is kind of a nice tool to have in your back pocket. You can check your answer, but if you get totally stuck and you have no idea, but you know how to take the derivative, you can still figure out the right answer. Okay, I think we've engaged in enough equine necro battery, right? We can move on. You guys know what equine necro battery is? That's beating a dead horse, right? That's the collegiate way of saying it. Okay, on to our last problem. So we want to find the general antiderivative of minus 8 times secant squared x dx. The book initially makes a point of putting parentheses around here, okay? Generally, most people wouldn't do that, but they're just trying to make it really clear that this is the function we're actually taking the antiderivative of. And again, I play the same game, right? There's a minus 8. That's a scalar multiple. I can take that out. And for the indefinite integral of secant squared, again, I have my choice, right? I can go to the formula sheet, or I can ask myself, is there a function that when I take its derivative gives me secant squared? Is there such a function? Victoria, do you think there is one?
Yeah, is it cotangent or?
You're close, you're close. So the cotangent goes with the cosecant, right? But what goes with the secant?
Just tangent?
Yeah, just tangent. Excellent. Yeah. Okay. And there we are. So we're going to get minus 8 tan x. And again, don't forget the c, okay? I think I told you guys, that the algorithms that create the possible question choices they're done by machine learning, and they know that students will leave this off, and they'll often tend to pick the first one that appears to be what they have. So very often they'll leave out the C and they'll put it as one of the first choices, right? So you go, oh yeah, it must be right because I got this answer and it's on one of the choices. not necessarily. Okay. That's looking pretty good. So I'll tell you what, if you guys want to submit that, and if you missed anything, I'll stick around and we'll kind of puzzle through and figure out what you did, okay? And if you got 100%, you're good to go. And if not, like I said, we can stay through, puzzle through it and figure it out, and you can still get full credit. These quizzes are designed for everyone to get 100 out of 100, okay? They're not designed to be tricky or anything like that, all right? I just want to make sure everyone has the basic skills,
Thank you, Professor. Have a good evening.
Absolutely, you too.
Thank you, Professor. Have a good day.
Appreciate it, you too.
Have a good day.
All right, thanks.
So Professor, with antiderivatives, you're saying there's no notation for it. What about a capital F of X equals and then the antiderivative?
No, there is notation for antiderivative. Yeah, no, absolutely. It's
Okay.
it's this right here, right?
Right.
And you're absolutely right. We haven't done this yet, but eventually we're going to denote small f as the integrand, and then you're right. Later on, we're going to start introducing capital F of X. However, you have to realize that to write this is not actually correct. Okay. We can't actually write it this way. So what we're going to have to do is we're going to have to modify this and make this T and make this a number and make this X. And that's why I haven't presented this yet, because it's a little trickier than that. But no, there is. I mean, there's definitely notation for antiderivative, and this is what we're going to use.
Cool. Thank you.
Absolutely. All right. Stay safe.
You too. Have a good afternoon or evening now.
Yeah, I know. They pretty much shot. Yeah. Hey, what's going on, guys?
I got question 2 wrong.
Yeah. Okay. Yeah. Let me go ahead and I'm going to give me a second. I can get in here and we can take a look and see what's going on. Give me 1 second. Ah, here we are. Okay. So Joel, let's see what we got here. Okay. Okay, so now I'm going to share screens and we can see what's going on. Okay. Here we go. All right, so first one looks good. And the second one, we ran into problems, right? Okay. Let's see. Yeah, see, so that was the question that Daniel was asking. Like, what do you write? Do you write y of x or y? Okay.
Yeah.
And so all you had to do is just put y. And that's why I'm doing this in class, so you don't get penalized when you're doing the homework, okay? And rest looks really good, man. Good work.
All right. All right. Have a good day.
All right, you too. Thank you. Hey, Theo, what's going on?
So I gotten 1 and 2 wrong. So I'm trying to figure out what I did wrong on those.
Yeah, let's take a look. Give me a second here. There you are. Okay. And there we are. Okay, so the first one, let's see what happened. So do you see what you did wrong here though?
I'm trying to figure out what I did wrong. I don't entirely see what I did wrong.
So you had 7t to the 6th. Now, when you integrate t to the 6th, that's a power function, right?
Mhm.
So what is the rule for integrating that? Here, let's go back here. I'm gonna stop sharing here. Okay. So this is the function that you're integrating, t to the 6th, right?
Mhm.
And the way that we're going to do that is we're going to use this rule that says if you're integrating a power function, well, what you do is you increase the exponent by 1, and then you divide by that same number, right?
Yeah.
So what would it be here, do you think?
Oh, so then would it be t to the 7 divided by 7?
Yeah. And then, of course, you were multiplying by a 7, so that would have canceled and you'd have been good. Okay.
Okay.
All right. Yeah, excellent. Excellent. Okay. So we got that one right now. Okay. So let's see. So in this one, oh, you know what? Okay. Do you know what you did wrong here?
I don't. I can't see what I put down.
Yeah. Okay. So here's what you answered. So you answered, I'm going to stop sharing here for a second. Where did that go? Okay, I'm not sharing anyhow. Sorry. Oh, let me share. Yeah, I thought I was sharing. I wasn't. There we go. Okay. Yeah. So here you can see now, right?
Yeah. Oh, so did I just need to put the y to y parentheses x?
No. You just put
Or
y,
did-
just y equals, right?
Oh, just y equals. Okay.
Yeah. So that again, that's what Daniel was asking. He said, should I put y to the x? I mean, I'm sorry, y, of x is equal to, or y equal to, or like you did, just the answer. And you have to put y equals to.
Okay.
All right, looking good.
All right.
Everything else good. Okay. Any other questions?
No, I think I'm good.
All right, you're free to leave, sir. Have a great evening.
All right. Thank you. You too.
All right, thank you.